Almost there. Section 4.5, sketching a curve. So we're going to put everything that we have learned together so that we can finally graph a curve that it is not easy to graph. For example, if we have to graph y equals 2x plus 3, that is something definitely we are perfectly capable of doing. However, all those functions that combine within themselves, trig functions or square roots or rational functions, or we are looking at denominators with logs, those are a lot harder to graph. So we have learned all the necessary rules to graph a very good sketch of them. So there's going to be some guidelines, things that we have to remember. And I want to stress this, things that we may not need to check for every single graph that we are looking at. So we're going to train to recognize for what kind of graphs we need particular things, and for what kind of graphs we probably don't need them all. So the first guideline is to pay attention to the domain of the function, because we certainly don't want to worry about numbers that we don't need to. For example, if I'm sketching a function of natural log, I know that the domain is all the positive real numbers, so I don't have to worry about how much the value of natural log is for negative numbers, because it's not part of the domain. So keeping the domain present is ideal, and that is going to be the first thing that we have to check. All this information can be read word by word, but what I'm saying is my take on it. The second thing that you may want to check are intercepts, and those are very easy, because if I'm trying to find the x-intercept, I replace y with 0 on the equation and then solve. And if I want to find the y-intercept, I replace x with 0 and then I will solve for y. And that's something that is very elementary. The third one is symmetry. And symmetry, although this is something that you don't need to test every single time, if I have an equation, for example, x squared, these are the kind of functions that are even functions, or something that has cosine in it. That's something that is another even function where the y's, whether they are positive or negative, it gives me the same answer. But this is not something that is going to be necessary. So this is probably one of those things that we may skip a lot of times depending on the exercise. But if we do know of a symmetry, if this is true for all the x's, so definitely whatever graph I have on one side, then I know that it repeats on the other side. It reflects over the y-axis, and this is called an even function, as you remember that. So if it has symmetry about the y-axis, then the graphs on this side reflects over the other side. And then if it has this other type of symmetry, if it's symmetric, for example, over or about the origin, then it's called an odd function. And you can see that if this is the first quadrant, what I have in the first quadrant repeats on the third quadrant, and what I have on the fourth quadrant repeats on the second quadrant, because the figure kind of rotates 180 degrees and one piece overlaps with the other piece. So this is symmetric about the origin, and that happens whenever I evaluate a function, and then you can see how the negative can actually come outside. For example, I have x cubed. If I replace x with negative x, you know that this is negative 1 x cubed, and negative 1 cubed is negative 1 again, and x cubed is x. So you kind of see when you evaluate negative x to the third power, then you compare these two, and this is like the opposite. So if the x's are opposites, then the y's are going to be opposites. So when you notice that, you know that it's another function, and it kind of rotates around 180 degrees and it replaces that. This is something that formally you wouldn't have to check, but this is something that I want you to keep in mind, especially when you have graphs that include some trig functions. if the domain is not specified. Usually they put 0 to 2 pi, sometimes they put 0 to pi over 2 and things like that. If this does not show, then assume that it's all real numbers, and definitely that's periodic. Now the next one is something that is very important, and those are the asymptotes. So remember, with horizontal asymptotes, you can either approach infinity or you can approach negative infinity. And if that limit actually exists, then you have a horizontal asymptote at that value. And if that's not the case, then you don't have a horizontal asymptote. But it still is good to know whether the function, if as x approaches infinity, y approaches infinity, so the function, you know, that will end like this. So that's important information to know anyhow, but you should keep in mind that you have to check for those. That is something that is necessary. Besides the intercepts, that's always something that we have to find out. Vertical asymptotes. In this case, whenever we know that we have a candidate for a vertical asymptote, for example, if I have x squared plus 5 over x minus 1, you know that x cannot be 1 because he makes the denominator 0. So that's a candidate for a vertical asymptote. So you just have to verify that from the left or the right of 1, the limit is either positive infinity or negative infinity. And if that's the case, then x equals 1 is a vertical asymptote. And this is something that we have seen before. I'm just summarizing everything that needs to be done and kind of going over some things that we have done in the past. Slant asymptotes is something that we have done in pre-calc, and they occur whenever I have a polynomial, I don't know, let's say degree 5, blah, 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 and I have another polynomial in the bottom of degree 1 less than the degree on the top. So if the difference of degrees is 1, then you definitely have an horizontal asymptote, and that can be found by using long division of this polynomial by this polynomial, and you're going to have some quotient at some remainder. Potato, tomato. Okay. You may not encounter this a lot of times, but when we do, then definitely ask for help if you don't remember. But it's very easy. It's just like long division. Intervals of decrease or of increase or decrease. Remember that we're finding whenever f prime of x is 0 or undefined, and then we want to know what happens. Let's say that it happens at 3 particular points, c1, c2, c3. If the derivative in all those points is 0, then I want to know what is the sign of the derivative. Is it a positive or a negative in each one of these intervals to see whether it increases or decreases. Then we have the local maximum and minimum, and this is also new. And you know, when you're taking the derivative, you find all your critical values, and then you want to see if the derivative changes sign from positive to negative or from negative to positive to determine whether it's a local minimum or maximum. Or, and that's what is called the first derivative test, or you can apply the second derivative test, and by which you can do the following. You find your critical values by making the derivative 0, and then on those values you evaluate it on the second derivative, and if that second derivative is positive, then you know it concaves up, and if it concaves up, you know you have a local minimum. And if the second derivative at that point at your critical value is negative, then you know that it concaves down, and therefore you will have encountered a local maximum. You can also do that at that point. But if it's 0, then you don't know what it is, so you have to use first derivative test. Now for concavity and points of inflection, you just find your second derivative and you equal it to 0. You find those values of x that make the second derivative 0, and those are your candidates for point of inflection. Then you just have to test, you know, let's say that this is your critical value. You have to test whether the second derivative is positive or negative, and if the concavity changes before the critical value and after the critical value, not the critical value for the first derivative, the one that makes the second derivative 0. If it changes concavity, then you have a point of inflection. And then the last step is just sketch the curve. It might be convenient for you to do a summary of these 4 pages so that you always keep it in mind and next to you when you do your exercise. Let me show you mine. This is not up for sale or for copies, but I have put all the guidelines that I have to keep in mind whenever I'm graphing, and the more I graph, the more I will remember everything that I need to consider for a sketch. Okay, those are my 7 items. For domain, I know what domain is, so I don't write anything. For intercepts, I know what those are and I don't write anything, but if you don't remember, then you can just write that down. X-intercept can be found when y is 0. Y-intercept can be found when x is 0. Then symmetry, that's something that formally I don't need to find out, and the equations sometimes are so complicated that symmetry is something that is very, unlikely that you encounter. It's not that it's unlikely out there. There's tons of functions. I don't know, like I can't find the exact probability. Anyhow, asymptotes. We have 3 kinds of asymptotes, and the horizontal is limit to infinity, and then the vertical asymptote is infinite limit. I'm approaching one particular value, and I want to know if I'm approaching actually positive infinity or negative infinity. Intervals of increase or decrease, I wrote my rule. I know if the derivative is positive, it increases. If it's negative, decreases. My local maximum, I put my 2 tests. First, I'm finding my critical values. Usually when I make my derivative 0, or when my derivative does not exist. And then I'm looking for to the left and to the right of that critical value if actually the derivative changes. So if it's from positive to negative, it kind of makes a sad face. So you have a local maximum, and if it changes from negative to positive, it kind of makes a happy face, and you have a local minimum. Or you can apply the second derivative test. So for all those values when the derivative is 0, you look at the concavity at that point. If it has a positive second derivative, you're looking at a local minimum, and if it has a second derivative that is negative, then you have to look at a local maximum. And the part with concavity, I'm finding all those values for which the second derivative is 0, and then let's say that I find 2, and then I'm looking whether the concavity changes, and concavity can only be seen on the second derivative. So if it's positive, concaves up, and if it's negative, concaves down, and if that particular point the concavity changes, then that's a point of inflection. And then I'm done. I summarize everything that I've known so far about functions and the characteristics, and I'm ready to graph. So generally all the problems are not going to be as long as this, but this is just to show you the guidelines and how they look like with a problem. So for domain, you know that the bottom can be factored out into x plus 1, x minus 1, because it's difference over squares. So from here you know that the domain is all the real numbers, but x cannot be 1 and x cannot be negative 1, but then everything else is good. X can take any other value. That's the domain. Then the intercepts, when you make x equals 0, then you have y equals 2 times 0 squared over 1 times negative 1, and this is 0. So you know that it crosses the origin, crosses the point 0, 0. So I know that about my function. Now when you make y equals 0, then since this is a fraction, the only way a fraction can be 0 is by making the numerator 0, not the denominator. So if you make the numerator 0, then that gives you x equals 0. So that's it. Like you're done with your intercepts. It's just giving you the same intercept for x and y. So, and that is true because when you're crossing the x-axis and the y-axis here, then it's both. So intercepts only one x-intercept, same as y-intercept. Now, for symmetries, this is something that you don't have to check every time, but then you have f of negative x would be 2 negative x squared, and then you have negative x squared minus 1. This is the original one. You know this is an even function, so that's the same, and this is also even function, so that's the same. So f of negative x ends up being the same as f of x, so you know the function is even, so therefore is symmetric respect to the y-axis. For the next one, then you want horizontal asymptotes or some kind of asymptotes. So you take the limit as x approaches infinity, either positive or negative, of 2x squared over x squared minus 1. Now notice how the fact that you're approaching infinity or negative infinity really doesn't matter because all the x's are raised to an even power, so this is a positive quantity no matter what. Now remember that I can this is a limit to infinity, and I have polynomials on the top and on the bottom, so I can pick the greatest power in the bottom and divide both numerator and denominator by x squared. So I have 2x squared over x squared over x squared minus 1 over x squared. So now these two cancel out and I have 2 on the top. Limit x approaches positive or negative infinity. And then I have x squared over x squared is 1 minus 1 over x squared. Now as x grows very large, this approaches 0. So this is 2 over 1, which is 2. So that means y equals 2 is a horizontal asymptote. Now for vertical asymptotes, there were some values that made the denominator 0. So those are the ones that I want to look at to the left and to the right. So let's look at first negative 1 from the left of the function. I don't want to write it down again, so it's okay for me to write f of x. So negative 1 from the left, maybe that was a bad idea. Just write it out because then you don't know what you're evaluating. So, and you have x plus 1, x minus 1. I want to write it as a... You already know that this answer is going to be either positive infinity or negative infinity. You just want to know which one it is. So as x approaches negative 1 from the left, that means that if this is negative 1, you have numbers that are very close to negative 1 but on this side. So a number like that will be positive here because, I don't know, pick negative 1.1, square will be positive. Now negative 1.1 plus 1 will be a negative value, and negative 1 minus 1 will be a negative value. So negative times negative makes positive, so this will be positive infinity. Okay, remember that we know it's going to be infinity, but we don't know if it's going to be positive or negative. Now let's evaluate the limit as x approaches negative 1 from the right of the same function, and then we're looking whether it's going to be positive or negative infinity. We don't know yet. That's why we have to do this little analysis about the signs. Now negative 1 from the right, being very close to negative 1 would be, I don't know, negative 0.9. Pick a small number, don't pick 0, that's too far. So this will still be positive because it's square, and this will be positive, negative 0.9 plus 1 is positive, and this will be negative, so this will be negative infinity. So that means that if this is an asymptote, this is just to give you a reference. I mean, I don't want you to make mini graphs every step of the way. But from the left is infinity, so I know it's going to go like that. And then from the right is negative infinity, so I know it's going to go down that way. So that's what the picture in your head as you're finding out these results. Now we're going to find the limit as x approaches 1 from the left of this, and it's easy to see it in a factor manner. This is positive no matter what. This is positive, it's 1 from the left. Think of the number 0.9, and 0.9 minus 1 is negative, so this is negative infinity. And then limit as x approaches 1 from the right of 2x squared over x plus 1, x minus 1. This is positive always. This will be positive. And 1 from the right, think of the number 1.1, minus 1 will be negative. So this is also, I'm sorry, positive. So this will be positive infinity. So now if this is negative 1, at 1, I don't know how they will connect, but I know at 1 I have a vertical asymptote, and from the left it's approaching negative infinity, and from the right it's approaching positive infinity. So you see it kind of starts coming together with all these results. Since we're talking about a rational function, if the degrees on the numerator and the denominator are not, the difference is not 1, then we don't have a slant asymptote. So since the degrees are the same, then I don't have to worry about slant asymptotes. The next item to worry about is intervals of decrease or increase. So we're going to find the derivative. Now this is an exercise for you. If you have 2x squared over x squared minus 1, you're taking the derivative, I'm sorry, this is f, and you're finding f prime of x. This is quotient rule, not L'Hopital. So derivative of the top for x times the bottom minus the top times the derivative of the bottom, which is 2x, and everything over x squared minus 1 square, because remember that you have to do that. So once you do this out and multiply everything that needs to multiply, and you this one with this, and combine like terms, you're gonna get negative 4x over x squared minus 1 square. So now you want to know when f prime of x is 0 or undefined. So in here you know that well, it's not gonna be defined at 1 or negative 1, but it's because it has asymptotes. It's not because the function has a minimum or a maximum there. So the only thing that you have to consider is when f prime of x equals 0, and that happens when x is 0, because remember, when I want a fraction to be equal to 0, I just have to make the numerator 0. So negative 4 times x equals 0, so x is 0. So I just have to, using the first derivative test, I'm going to show you the difference between that and the second derivative test. With the first derivative test, then I have to know what happens before 0 and after 0 with the derivative. Okay, I want to know what is f prime of x. So before 0, let's say negative 0.5. If x is negative 0.5, this product will be positive. And since this is raised to the second power, this always be positive, so the result will be positive. And then what happens to the derivative after 0? Okay, think of the number 1, for example. Then if x is 1, this product is negative, divided by a positive is negative. So if the derivative changes from positive to negative, then you're looking at this to be a local maximum. So local maximum at x equals 0. But how much is that maximum? Now you have to find what is f of 0 on the original. So f of 0 will be 2x squared over x squared minus 1, and when the x is 0, then this is definitely 0. Now let me show you with the second derivative. With the second derivative, I'm just going to take the derivative of this. Again, quotient rule, it would be negative 4 times the bottom, x squared minus 1 squared, minus the top times the derivative of the bottom, which is 2x squared minus 1 times 2x, I'm using chain rule on the bottom, over the bottom square. Square of a square is to the fourth. So this is negative 4x squared minus 1 plus, and I'm gonna just clean this up, 4x times 2x is 8x, sorry, times this 2 would be 16x squared times x squared minus 1 over x squared minus 1 to the fourth. Okay, now I found out that when x is 0, f prime of 0 is 0. So I'm gonna evaluate this number into here, and I wanna know what the concavity is at 0. So f double prime of 0 ends up being negative 4. This is 1 plus this is 0 squared, and it makes everything in here 0. And then this is 0, then this makes this 1. So this is negative 4. Since the second derivative is negative at 0, then that means it concaves down, so you have a local maximum, which is the same result that you have from the first derivative, that at 0 you have a local maximum. Now the last thing to see is the concavity. And well, the concavity has to deal with f double prime. The way that we left it before needed some cleaning up a little bit. And so first you will do this square of the binomial. Remember that is the first one is square minus double the first times the second plus the second one is square. And then I distribute the negative 4. Please do this exercise on your own because I want to make sure that you do the algebraic simplification correctly before you move on. Then you combine like terms. Then you have this trinomial, and this factors out. First you have a greatest common factor of 4, and then this factors out. Treat this as if you had 3x squared minus 2x minus 1, and this is something that you have factored to death before. So instead of x squared you have x to the 4, instead of x you have x squared, and then instead of factoring out as 3x plus 1 x minus 1, it would be 3x squared, but it's the same thing. So you cancel out one of these factors because they are the same, and then you have 12x squared plus 4 over x squared minus 1, and now to the third power. So that's what f double prime of x is. Since you want to see how the concavity changes sign, you know that this is not going to be 0 ever. So you know that you're going to have some asymptotes that are going to break up your graph. Remember, a negative 1 and 1. And you know that you have a local maximum and 0 because the concavity is positive. So f double prime here is positive. It's negative, and that's why you have a local maximum. Then you want to see how is the concavity here and here, because there is no more breaks on your graph, and there is no other numbers for which this is 0. So you just want to know how this behaves to the left of negative 1. So to the left of negative 1, it's okay to pick a number far away like negative 2. So in here, negative 2, this will be positive. Negative 2 here will be positive. Minus 1. Positive, and then cube positive. So this is positive. And then when you have, let me see. When you have a 1 that is to the right, a number to the right of 1, then in here you have, I don't know, 2 squared, this is positive, this is 4 minus 1 is 3, cube is still positive, so this is also positive. So you know that this concave up here, and it concaves up here, and in here it concaves down. So now you know how it behaves, and then we're ready to do the sketch. Okay, so with so much information, what needs to be done first? So first you sketch your asymptotes. I have 1 at x equals negative 1, and at y equals negative 1. and then you have a horizontal asymptote at 2. The other thing that you know is that you have a local maximum at 0. So since this is a local maximum, you know that that's the highest point around that. And then you also know the limits as x approaches -1 from the right, and as x approaches 1, from the right, and as x approaches 1 from the left, and both of them were -infinity. So this does make sense that it's going down like this. Now, you know the concavity in here, the concavity is it opens up, and it opens up here. So you know that those graphs are going to open up on this side and on this side. You also know that as x approaches -1 from the left, it goes to infinity, and the same as from the right of 1. And so since this is concaving up, so it is not like this, it goes like that. So it goes up like that. And then this is also a horizontal asymptote, so I know that it's not going to cross that. It's just going to keep getting closer and closer. And then isn't my graph beautiful? Oh, and it matches the one in the book. Look at that. So this is nice, and this is very consequent with everything that we have found so far. It does look a little bit hard at first, but I promise it will get easier. So good luck with the rest of the slides.